Hi there. In this video, I want to talk about something that confused me for quite a while. How are people running multiple AI agents, opening multiple PRs, and merging everything without constantly breaking their code base? Lately, I have seen a lot of people sharing their AI agent workflows, tens of agents working at once, opening multiple PRs, sometimes an absurd number of PRs being merged in a single day. And every time I saw that, I had the same question. How the hell are they doing this without constantly breaking things? Because each PR can look perfectly safe on its own, but those PRs eventually have to meet inside one shared code base. So how can tens of individual green changes still combine into one working main branch? I could not connect those demos to the way I personally used agents, and that confusion is what sent me down this rabbit hole. My confusion was personal because I had already tried parallelizing my own work with agents, but my version looked very different. Usually, I would have multiple agents working on completely different projects at the same time. One agent on one project A, another on project B. Since they shared no code, there was basically no chance of a conflict. If I wanted agents working on different features inside the same project, I would ask each one to create and work inside a separate work tree. Again, from my point of view, there was no chance of them overwriting one another while they worked. The obvious overhead arrived later, when all those isolated changes had to come back together. So I understood parallel coding, but not how people were integrating tens of PRs without the same merge time pileup. That was the exact gap I wanted to understand. Before I could make sense of the solutions, I realized I was mixing three different jobs together. So I needed to first clear up the distinction between these first. A work tree only gives the file system isolation. It stops two agents from overwriting the same local working directory. A branch gives me history isolation. It stores each agent's changes as a separate diff against the commit where that agent started. Integration is the separate final job. Combine those changes and prove that the resulting system still compiles, passes tests, and behaves correctly. My work trees were solving the first problem, while my confusion was actually about the third. Once that became clear, I started my research at the first place. Those isolated branches began to diverge their base commit. The first thing I found was that every branch is a diff against one frozen commit. Here, both agents start from commit A. While they work, main receives commit B, then C, then D. The agents are still isolated and their code may still be correct, but their shared understanding of the repository is getting older. This distance is branch drift. The longer branches live, the more assumptions can change underneath them. Function names, schemas, dependencies, tests, or surrounding behavior. What I found was that I had also been treating every conflict as the same. The obvious one was textual conflict. Two agents edit the same line, git cannot choose, and the merge stops. This is annoying, but at least it is loud and visible. At the same time, Agent B adds a toolbar button that calls send reply. The changes touch different files. Both branches can pass these checks that existed on their old base. Git merges them without a complaint. Then the application runs and fails because send reply no longer exists. No merge conflict screen catches this because there is no textual conflict. The combined code has to be rebuilt and retested. At this point, the problem finally felt concrete. Branches can become stale and Git cannot verify behavior. Now, the solution started to make sense. The first solution that made sense was a merge queue. It takes the file of individual green PRs and turns integration into a controlled sequence. The queue takes the first PR, rebases it onto the latest main, includes everything already merged ahead of it, and runs the tests again. PR number 1 passes, so it becomes the new main. PR number 2 had green on the old base, but when tested with number 1, it conflicts or breaks the build. The queue ejects it before it can poison main. Now number 3 does not blindly follow number 2. Its effective base is rebuilt from the surviving chain. It reconnects to number 1, gets tested against that real state, and only then merges. The queue does not eliminate conflicts. It makes them small, current, and unable to silently enter main. That solved the independent PR case. But one of my original questions was still unanswered. What if PR number 2 genuinely depends on code from PR number 1? That dependency question led me to stacked PRs. Some tasks are naturally a chain, and pretending they are independent creates awkward branches. Imagine three pieces: a snooze API, a toolbar button that calls that API, and a snooze folder that depends on both. You could wait for each PR to merge before starting the next, but that wastes parallel capacity. So you could put everything into one giant branch, but then the review becomes painful. A stack keeps the dependency explicit. Number 2 branches from number 1, number 3 branches from number 2, and all three PRs stay small. Once I saw the stack as a dependency chain, the movement on screen made more sense. These are not three unrelated PRs waiting in random line. Each one carries the work below it. First, number 1 joins main. Notice what remains. Number 2 still depends on that API, and number 3 still depends on both changes below it. The number 2 is replayed onto the new main and tested with number 1 actually present. If that combined state works, number 2 can join main too. Number 3 follows the same path. So what the stack gives me is not a magic bulk merge. It keeps dependency order visible while each small PR is retested against the base that now exists. That extra structure only makes sense when the dependency is real. Unrelated work still belongs in separate PRs. So stacks answered the dependency problem. But there was one more case. A feature might need weeks of work, while I still want its code integrating continuously. That led me to the third pattern. The third pattern I found was a feature flags. They solve the case where code should integrate now, but users should not see the feature yet. A feature flag separates integration from release. The unfinished implementation can merge continuously while the flag stays off. That keeps the code close to the main and lets every new piece be tested with the rest of the system. When the feature is ready, turn the flag on. If the production behavior is wrong, turn it off again without trying to reverse a giant chain of commits. The important mental model is simple. Merged does not mean released. Once those become separate decisions, long-lived feature branches become much less necessary. After going through all three, I finally had a much cleaner map of which tools solve which kind of parallel work. After going through all three, this is the decision map I ended up with. Use a merge queue for independent PRs that are all ready but may invalidate one another as main changes. The queue gives them a safe integration order. Use a stack when the dependency is real. If the toolbar cannot exist without the API, encode that relationship instead of pretending both branches came from main. Use a feature flag when code should separately integrate early but the user facing feature is not ready. So I do not need every tool in every repository. I first ask whether the work is independent, dependent, or simply incomplete. Then I use the smallest mechanism that makes that relationship explicit. With that map clear, I could turn the research into the agent workflow I would actually use. From that research, this is the practical loop I would now use for parallel agents. Start with one small task. Give it one short-lived branch and one worktree. Let the agent make the bounded change. Before integration, rebase onto the latest main. Run the real build, test, or application behavior on the new base. Merge exactly one change. Main has now changed, so every remaining branch goes through rebase and verification again. An agent can resolve a bounded textual conflict, but it should not guess through an ambiguous product decision. The loop stays the same whether I have 2 agents or 20. More agents can increase parallel production. Safe integration still happens one verified step at a time. And that look took me straight back to the question that started this whole deep dive. That finally answered my original question. The teams showing tens of agents and tens of PRs are not living in a world without conflicts. They are controlling where conflicts appear and how large they are allowed to become. They keep tasks small, they keep branches short, they make dependencies explicit, they separate merging from releasing. Most importantly, they retest every candidate against the main branch that actually exists now, not the one that existed when an agent started. So the key takeaway is not merge n things at once. It is merge one thing n times against the real current base. That is how parallel agents increase throughput without turning much time into chaos.